Alright, so right here with this particular problem, we are tasked with finding the equation of the elastic curve and then the slope and then the deflection. There are some things that we should notice before we even start anything at all. And then the slope, we know it to be the same as theta, which is the same as the y derivative, right? And then for the deflection, if you don't see just deflection, but you just see y a or yb or something, meaning that we are finding the deflection as those points, right? So this is theta, and then this is y derivative, right? And this is an equation that we have again. And then looking at the diagram here again, we get to see that the coordinate system is very important. But generally, what we are doing here, we are what do you call it? We are placing our origin here. So then our x is in this direction, y is in this direction. That's also very important, right? And then the equation of the elastic curve, the general one is something of this sort, where we have mx, right, and then we have ei y second derivative, right? This is the general equation. So then there's a force P applied here, right? So then if something will happen, there'll be because there's a cantilever, right? The support is only on one side. We have something of this sort. This will be the initial position of the cantilever. This is the support, and then it deflects this way, right? Something of this sort when the force is applied here. Right? So that's what will happen. When you have this in mind, it makes your work much more easier, and then you can flow, right? So now let's do it. We do the free body diagram. We'll get something of this sort. Let's see. This is a free body diagram, right? So this, a minute. So we get this, right? And then we have our reaction here. Reaction at B, right? This is point B, and this is point A, right? And our coordinate system is somewhere here. This is y, and then this side is x, right? We know the whole of this length, sorry, the full length of the cantilever to be L, right? Yeah, this is the free body diagram. But then here's a case where we want to actually find these things. But then looking at this again, we have how many, what do you call it, load, support, moment, and stuff. We have only two, one, and then two. This is very important because, like, if you don't know the number of them, you won't be able to know the number of sections you should do, right? So we have 1, 2. So then the number of sections we can do to find whatever that we need is just one, right? So let's see. So just one section, we choose where it is. So let's say we make a section, right? Something of this sort. There's a free body diagram. There's a section point. Let's name that D. The full length of this particular section here, let's see x, right? And then again, our coordinate system very important. If you have that in mind, there's no need for you to draw it, but like just to make sure we are on point, we draw it, right? And then the shear force V, the momentum here is what m, and then the force applied there P, let's put it here, right? We know that at this particular point D here, we know the momentum there, the sum of the momentum around about that particular point is 0, right? So then if we try doing that, we know that we have m, right, is a momentum, and then we have plus p, the distance with respect to this point here is x, so right, so p times x is equal to, should be 0, right? That's it, the momentum. But then we know this m here to be this, right, ei y derivative, so that's what we end up having, ei y derivative second derivative plus p x 0, right? That's what we have. And then our aim is to do what? To find the equation of the elastic curve, right? And then to find the slope, and then to find the deflection. Looking at this very well, we know that the slope is y derivative, just first derivative, right? So we have to do just one integration, first step. And if we want to find this deflection here, which is generally just y, we do double integration, right, to find that one. Are we okay? So now let's move on. So now that we have this, if we try to find the equation of the slope, let's see. This is the general equation for the slope, right? For what we have here in this particular diagram, this is how it to be, right? So if we move on and we try to do the integration, like just put it on let's try and separate the terms first. Y second derivative equal to minus p and then x, right? This will be negative, very important. Now to find the, so let's see, this is equation 1, right? And now to find the slope, which is the first derivative, we do integration, right? We end up getting e I y first derivative, right, and then minus p, right, x squared on what, 2, right, and then we get what, plus constant. Let's label the constants so that our work is easier. This is equation 2, right? And the one important thing is that whenever you find, what do you call it, do your integration and get a particular constant, it's much more convenient if you find the constant at that very moment, because the more you do the integration, the more constant you get, and then your work can become cumbersome. But here's the case where we are doing it step by step, right? So whenever you get a constant, try and find a way to find what that constant is, right? Looking at this very equation, this is the way to find the constant when you get it, right? Looking at this very equation, right? This is what we do. Before we know that this E here, Young elastic modulus, is a constant, right? It can be given. I here is a sectional, what do you call it, constant, depending on the beam or whatever. This Y here is mostly what we are trying to find, right? Y derivative or just Y, right? This P here is a force, a constant. The only thing that's changing is X, right? So then we call some of the boundary conditions. When you're able to ascertain the boundary conditions, you can find the constants with ease, right? So let's do it this way. So to do that, you go to your diagram, right, and you find the boundary condition for the X, right? So let's see. So the only thing we can change at this particular point, we know this is a constant, right? This is a constant. The only thing we can change is this Y here, Y derivative, not just Y, and we have X, right? So let's see what we can do about that. To do that, you go to the diagram, right, and then we do our best to make sure that Y is something and then X is something, right? So let's see, at the point where we have X to be, let's see, so right, there's a deflection. If it happens, there's a deflection. So let's say, and we know yi is the slope, right? Right, and where would the slope be 0? Looking at this point here, when there's a deflection, right, because of this force here, there will be a slope here. But at this particular point where the beam is attached to the wall, there won't be any slope, right? So at that point, we can say at point B, because looking at the diagram, this is point B, right? So we can say that at point at B, right, we have X to go at this point B. Then again, this what do you call it, the original diagram, this what do you call it, coordinate system. X goes in this direction, so at the time I get here, X will have gone the full length of the beam, right? So at the point where X is equal to L, we have our y derivative, which is the slope, to go 0, right? The moment you have this, you can place them in the equation. So this is what we have: EI to bracket 0 equal to minus P times x squared. X squared is what? L. That's squared all over 2 plus C1. Now you can find the C1. Here becomes 0. So then we end up getting our C1 to be equal to what? PL squared on 2. This is what we have. Alright. You have it. Now you put it in the equation. Equation 2. So we end up getting something of this sort. E I y derivative equal to minus px squared on 2, right? And then we have plus pl squared on 2. This is another equation. So let's say equation 3, right? Yeah. So now that we have this, generally then again, don't forget your aim. Our aim is to find what? The equation of the elastic curve, which we found, and then the slope, theta or y derivative, right? Now that we have something in terms of y derivative, we can find y derivative giving us our slope, right? So making y derivative the subject, we have something of this sort. Y derivative equal to 1 on EI, right? 1 into bracket, negative, very important, px squared on 2 plus pl squared on 2. This is the general equation for the, what do you call it, what's the name, the general equation for the slope when we've not actually defined the point that we want to check the slope for, right? So if they say a point A or point B, that's when you substitute x and L and whatever, right? And then if the constant E, I, and P are given, you put them into, right? But this is the general equation for the slope for this particular system, the cantilever that we saw earlier, right? Now that we have this, now that we have this, we can still do some integration and get y, which will give us the deflection, right? So that we'll get something of this sort. So let's say this is equation 4 too, right? So let's say equation 4. So we have EI, right, y. Now we are doing integration again. Px cube on what, 6, right? And then we have PL squared x on what, 2, right? And then we get another constant C2. Whenever you get a constant, I'm repeating this, whenever you get a constant, it's wise to find that constant before you continue. It makes your work easier and clear, right? Then again, we have C. Looking at this equation, not for us to find a constant, we find a way to make the things that we can change 0 or something, right? So this constant, again, this constant, P is constant, P, L is also constant. The only thing we can change is, well, Y and then X, right? So let's see. Our aim is to find C2, right? So let's see how we can go about this. Y. At the point B, when you look at this again, even after the deflection, at the point B, we will still have a deflection to be 0, right? Because this will move, but if we were to be at the point, let's say point A, after deflection, there will be some sort of the beam moving down, right? But at the point B, it won't change, right? We'll still have what's the name? Y, which is the deflection, to be 0, right? Because at here, which is the point B, let me do this again. Here's A. Here's A. The 3-point diagrams are very important. It makes your work more easy and clear, so you don't have to be thinking that much, right? You can just follow your diagram. So our point B is very clear that even after deflection, we have our Y to be 0, right? And at the point where we have our Y to be 0 here, that's where X has gone the full length here, right? So we have this, right? So now let's go and put it in there and see what we get. So we can go again and see something like at B, we have Y to be equal to 0, and then X is equal to L, right? So we go and then put in whatever that we have. We have E, yellow. So then we have E, I, 0 here, right? The minus P x cubed on 6. We have a value for X, so let's put it in, right? So L cube, right? Minus, very important, plus P L squared, and then we have another L here on 2, right? Did we get? Yeah, so our aim is to find C2, right? So let's see what we get for C2. Here becomes 0. All this becomes 0, right? And then let's see. Our C2 will be L cubed, so that will be minus 1 on 6 plus 1 on 2. So let's see what we get for that. Minus 1 on 6 plus 1 on 2, that gives us 1 on 3, right? So let's move on. We end up getting our C2 to be, this is 1 on 3, right? So if we bring it to the other side, it becomes minus, right, PL cubed on 3. This is our C2. Now we put it back in here, and then we move on, right? So let's see what we have. We have EI y equal to minus P x cubed on 6. Minus, very important. If you don't bring it there, it's a whole new scenario. PL squared on 2, right? There's an X. Everything should be there. Now we have our C2, right? And there's a minus. So minus PL cubed on 3, right? We can factor this out. Let's see how we go about it. We end up getting something like this. So 1 on 6, right? And then we have a P here, right? P. So what we get inside will be S cubed, and then we have 3 here. 3 L squared x, right? What do you have again? Minus 2, right? 2L cubed, right? So this is what we have, right? When we try to find out just y, we'll get something on this, so p, right? So we get p on ei 6 here, right? Where's the minus here? We didn't bring it. If you don't bring it, it's a whole new case, right? Here's actually plus, here's minus. So we get minus x cubed plus 3l squared x minus 2l cubed, right? This is what we have. Then again, this is a general equation for the deflection, but when you have to find it at a particular point, then you do the boundary conditions and then you find it, right? So now let's see, these are the equations, right? This is another equation, equation 1, equation 5, right? So let's say we want, what's the name? This is what deflection, right? Yeah. Let's say we want deflection at A, right? So we go back to the diagram, or if you put a diagram with the deflection stuff, and we're like at A, we know x to be equal to 0. So let's see at A, let me send the color. At A, x is equal to 0, right? So at A, x is equal to 0, and then y is equal to what? Just 4y, right? We can't determine that. But at B, we know x to be equal to the full length of the bar, right? So these are some of the things, right, that you can do. So now that we are trying to find the deflection at A, we know that at that point, then again, another thing, if you are trying to find something, so let's say you are trying to find y, deflection at A, you look at the equation, what do you need to actually find the deflection? We know P is a constant, E is a constant, I is a constant, right? L is a constant. The only thing we have to actually find is x, right? So we know that at point A, in this particular one, we know that x is equal to 0. So that's the only thing you have to do. Just put that in and then get it, right? So y at A, which is a deflection, we know that. Let me write it. Let's see. So at A, so it's clear when we do it this way. So let's see. To find this, we know that at A, we know x to be equal to 0. So that's the only thing we do. So ya, or deflection at A is equal to P on 6ei, right, minus 0. I'm just doing this so that we see it, but the moment you get your values, you can just go straight forward, right? 3l squared to bracket 0, right, and then 2l cubed, right? So this is what we do. So this tends to 0, this is 0, right? We're now getting y at A. You're now getting y at A. Y at A being minus, right? P. Let's do this again. Minus 2p L cubed on what? 6ei, right? So that's what we have for deflection at A, right? If you are trying to find the slope, what is the slope? The slope is theta, or what's the name? Y derivative, right? We have the equation already, right? So you look at the equation, what do you need to find that? We know the rest are constant. The only thing we can change is x, right? At A, we know x to be 0, so you just put it in. So let's see. Let me copy this. Okay. All right. So before you find something, you know the equation already. What do you need to find whatever that is in the equation? That's what you do, right? Let's bring this here back. Yeah, so now we have it. So let's see what we can do. The only thing we can change is x, right? And at A, we know x is 0. So you put your 0 in. Alright, so let's click on this. Oh. Okay, let's see if we can clean this. Oh yeah. here's x, right? The equation itself was squared, right? I'm trying to find slope. Yeah, squared. So squared, and then we know our x equals 0. Let's put it in and see, right? Now you have that, right? So we end up getting, and then it's good to write it this way. Yes, slope at a. So slope at a, which is theta a, y derivative a, whatever. You end up getting this tends to 0. So you end up getting p l squared, right, on 2e I. That's what we get, right? Yeah, so that's what we get. So now we are trying to find it at different points. Let's say point B, right? So if we are trying to find the deflection at B, then again the same equation. So now let's even write this first. Before you do anything at B, you have to write it. At B, the boundary conditions, right? At B, we have x to be equal to the full length of the beam, right? At that point is the full length, right? And we have yes, and then we have at that point we have our y, which is the deflection to be 0, and then we have our y derivative, which is just y. But looking at it, we only need this what do you call it, the x to find it. So let's find the theta b first. Right. Theta b. So this is slope, right? Yeah, slope at b. At b. At b. Right. Well, this is just theta. So let's see our theta b, which is a slope at b, is equal to 1 on ei, right, to bracket minus p x. Our x is L, right? So L squared on 2, man, very important, plus p L squared on 2, right? So that's what we get for theta b, or the slope at b, right? So here, this plus this, right? They are the same, it tends towards 0. Here I'm getting 0 for theta b, right? So now let's do the deflection at b, right? Deflection at b. Let's get the equation. Deflection is just y, right? Where's y? Y. This is our y. This is our y. So let's copy that. Then again, before you find it, you find the equation already. What do you need to find what you want, right? And then you put it in, or the boundary condition, you look at the diagram, you get that, and then you move, right? So this is our y, right? This is just our y. Hey, let's look at it again. Yes, this is our y. Our y, right? So y at b, what do we get? P on 6ei, right? To bracket at b, our x is what? L, right? So minus L, the minus is not part of it. L cubed, right? Plus 3L squared times L, right? Minus 2L cubed. Let's put this in all. Minus 2L cubed, right? So now, using that L, that's what we get, right? So let's see, what do we end up getting? This is a cube, this is a cube, this is a cube. We can add them, right? This is 2 minus this is 0. So we end up getting 0 for all this, right? Because this is 3, right? This minus, we end up getting 0. So our y at b becomes 0, right? Because all these becomes 0. So 0, right? Yeah, so that's what we get.